astronomers combine mathematical models with observations to develop workable theories of how the universe came to be. The mathematical underpinnings of the Big Bang theory include Albert Einstein's general theory of relativity along with standard theories of fundamental particles. Today, NASA spacecraft such as the Hubble Space Telescope and the Spitzer Space Telescope continue measuring the expansion of the universe. One of the goals has long been to decide whether the universe will expand forever or whether it will someday stop, turn around, and collapse in a big crunch. According to the theories of physics, if we were to look at the universe 1 second after the Big Bang, what we would see is a 10 billion degree sea of neutrons, protons, electrons, anti-electrons, positrons, photons, and neutrinos. Then, as time went on, we would see the universe cool, the neutrons either decaying into protons and electrons or combining with protons to make deuterium, an isotope of hydrogen. As it continued to cool, it would eventually reach the temperature where electrons combined with nuclei to form neutral atoms. Before this recombination occurred, the universe would have been opaque because the free electrons would have caused light, photons, to scatter the way sunlight scatters from the water droplets in clouds. But when the free electrons were absorbed to form neutral atoms, the universe suddenly became transparent. Those same photons, the afterglow of the Big Bang, known as cosmic background radiation, can't be observed today. NASA has launched 2 missions to study the cosmic background radiation, taking baby pictures of the universe only 400,000 years after it was born. The first of these was the Cosmic Background Explorer, COBE. In 1992, the COBE team announced that they had mapped the primordial hot and cold spots in cosmic background radiation. These spots are related to the gravitational field in the early universe and form the seeds of the giant clusters of galaxies that stretch hundreds of millions of light-years across the universe. This work earned NASA's Drive. John C. Mather and George F. Smoot of the University of California the 2006 Nobel Prize for Physics. With greatly improved resolution compared to COBE, WMAP surveyed the entire sky, measuring temperature differences of the microwave radiation that is nearly uniformly distributed across the universe. The picture shows a map of the sky with hot regions in red and cooler regions in blue. By combining this evidence with theoretical models of the universe, scientists have concluded that the universe is flat, meaning that, on cosmological scales, the geometry of space satisfies the rules of Euclidean geometry, e. g. Parallel lines never meet, the ratio of circle circumference to diameter is pi, etc. A third mission, Planck, led by the European Space Agency with significant participation from NASA, was launched in 2009. Planck is making the most accurate maps of the microwave background radiation yet. With instruments sensitive to temperature variations of a few millionths of a degree and mapping the full sky over 9 wavelength bands, it measures the fluctuations of the temperature of the CMB with an accuracy set by fundamental astrophysical limits. One problem that arose from the original COBE results, and that persists with the higher resolution WMAP data, was that the universe was too homogeneous. How could pieces of the universe that had never been in contact with each other have come to equilibrium at the very same temperature? This and other cosmological problems could be solved, however, if there had been a very short period immediately after the Big Bang where the universe experienced an incredible burst of expansion called inflation. Whatever its nature, the inflationary model predicts that this primordial energy would have been unevenly distributed in space due to a kind of quantum noise that arose when the universe was extremely small. This pattern would have been transferred to the matter of the universe and would show up in the photons that began streaming away freely at the moment of recombination. As a result, we would expect to see, and do see, this kind of pattern in the COBE and WMAP pictures of the universe. But all this leaves unanswered the question of what powered inflation. One difficulty in answering this question is that inflation was over well before recombination, and so the opacity of the universe before recombination is, in effect, a curtain drawn over those interesting very early events. Fortunately, there is a way to observe the universe that does not involve photons at all. Several missions are being considered by NASA and ESA that will look for the gravitational waves from the epoch of inflation. During the years following Hubble and COBE, the picture of the Big Bang gradually became clearer. But in 1996, observations of very distant supernovae required a dramatic change in the picture. It had always been assumed that the matter of the universe would slow its rate of expansion. Mass creates gravity, gravity creates pull, the pulling must slow the expansion. But supernovae observations showed that the expansion of the universe, rather than slowing, is accelerating. This stuff has been dubbed dark energy, but to give it a name is not to understand it. Whether dark energy is a type of dynamical fluid, heretofore unknown to physics, or whether it is a property of the vacuum of empty space, or whether it is some modification to general relativity is not yet known. Thanks for your watching again. Please like, subscribe to watch more videos, and let your feedback at comment below.